Okay, so welcome to Psych 101, General Psychology. Today we are covering the second part of the psychological research chapter. So we need to talk about experimental research, and we need to talk about correlations and how to analyze research, stuff like that. So let's begin with experimental research. What is experimental research? What is an experiment? Okay, it says here, an experiment is a study where the researcher manipulates one variable to determine the effect on another variable. That's a technical definition. What that really means is that an experiment is a study where you basically vary one thing to see what it does to another. To put it simply, it's a study about cause and effect. It tries to get at cause and effect. We do one thing to see what happens to something else. That's the simplest way I can describe an experiment. Okay. So in an experiment, you actually do something to participants, okay? You actually do something to them. There is some manipulation. Here's an example. An experiment, okay? You vary alcohol to study aggression. That is an experiment. You are varying something, you're manipulating something, and you want to see what it does to something else. You want to see what it does to aggressive behavior. So alcohol is the cause, that is what we're manipulating, and aggression is the effect. That is what we call an experiment. An experiment is a study that basically tries to get at cause and effect. Right away, I'll tell you about the strengths of about an experiment. An experiment, could potentially give you cause and effect, could potentially demonstrate cause and effect. That is the most important thing about an experiment. That is why we do experiments. We want to show that one thing causes another. And it's the only kind of research method that actually does that. All the other ones we talked about, the survey, the observation, the case study, the cross-sectional study, the longitudinal study, those do not demonstrate cause and effect. This one does. It's designed to do that very thing. So one of the strengths about the experiment is that it can potentially demonstrate cause and effect. And another thing is that you have control over the variables and the environment in an experiment. You control, for instance, precisely how much alcohol participants are going to get. And you can determine that based on their weight, for instance. You control the environment. Usually experiments are done in a laboratory, and you isolate your participants. And you make sure that the only thing that can happen is that participants consume some alcohol, and then they have some opportunity to behave aggressively. And that control is important. That control actually is what allows for cause and effect. We control the independent variable. Getting ahead of myself here with some terminology, but we control the cause, okay? We control what happens. We isolate participants, okay? We control the cause so that we can then study the effect. So that control allows us to determine that A led to B, that the cause led to the effect. And that is important. So those two things are related. Cause and effect and control of variables in the environment are related. And those are some of the most important strengths of an experiment. They allow us to demonstrate cause and effect and to control the variables in the environment being studied. Let's keep going. There's a lot of potential weaknesses to an experiment. We'll talk more about how to do an experiment in a moment, just some features of an experiment, but I'm going to tell you about the weaknesses right away. There's a lot of potential weaknesses to an experiment. If you don't know what you're doing, some of these will be a big problem. Okay. One thing about an experiment is that it can be very time consuming. Experiments in general are time consuming. There's often not much you can do about that. Experiments can take weeks, months, or even years to complete. It's not something usually that you can do in just a few hours or a few minutes. Okay, very time consuming. And experiments are also usually very expensive. Well, they take a long time, and guess what? People need to be paid. There are assistants, there are other researchers, there's the whole team involved in the experiment. Those people need to be paid. Often when you do an experiment, participants are also paid for their time. And when you do an experiment, it's not on one person. you do an experiment and at least dozens of participants, and they need to be paid for their time. There's equipment that has to be bought. There are, resources. There's all kinds of other things. I'll give you an example. When I was in graduate school, my research involved the effect of alcohol on aggressive behavior. My research involved what's called intoxicated aggression. In other words, I studied the effect of alcohol on aggressive behavior. Okay, so guess what? There was alcohol that needed to be bought. Okay, there's also equipment that is used. There's also equipment that is used to determine if participants are actually intoxicated, if they're actually drunk, a breathalyzer. Okay, and those things are very expensive, by the way. And there's also there are also tools, machinery that is used to calibrate the equipment to make sure it's measuring the amount of alcohol in people's breath precisely. There were assistants that needed to be paid. There are the researchers, and there was a clinical psychologist involved that needed to screen the participants to make sure that we're studying healthy participants who can safely consume alcohol and not alcoholics. And that person needed to be paid for her time. It was a female in this case. There were pregnancy tests involved. If female participants wanted to participate, they had to show that prove that they were not pregnant. So there was a female assistant who told them, okay, you need to prove that you're not pregnant, so take this pregnancy test, come back and report to us what the test says. So there's all this stuff that goes into an experiment, and it gets expensive really fast, okay? They can cost thousands, tens of thousands of dollars, or even hundreds of thousands of dollars. Okay, they're very expensive to do. Another problem with experiments is that they're usually done in an artificial setting. They're usually done in a laboratory. And because it's an artificial setting, participants may not be themselves. They may not behave naturally. That's related to another weakness that's labeled there, that's in bold, the observer effect. There are changes in participants' behavior due to awareness that they are being observed. So because participants know that you're going to be messing with them in some way, they may not behave naturally. They come into the laboratory, they're going to participate, and it feels to them like, like they're in the doctor's office, in the dentist's office or something like that, and they're not quite themselves. So that's the observer effect. They know they're being observed, they know that we're going to be doing something to them, and they may not behave naturally. Let's keep going. There's other weaknesses. These are a little bit harder to understand. Other potential problems. In an experiment, there could potentially be what we call confounding variables. That sounds complicated, but a confounding variable is some other thing that could affect the outcome of the experiment. So let's say you're studying the effect of alcohol on aggressive behavior. You want alcohol to cause aggressive behavior. That's what you want. But if you're not careful, there could be some other thing that is actually causing the aggressive behavior and not the actual alcohol. Give you an example. When I was doing my study on alcohol and aggression, the participants that consumed alcohol had to participate in it took them 4 hours, basically, of participation to get through the whole thing. It took them about 2 hours to go through the experiment, okay? And we gave them some alcohol, okay? And then they went through the experiment, and then afterward, we had to give them time to sober up, another 2 hours for them to sober up, because we're not allowed to release them drunk, basically. So those that consumed alcohol got to participate for 4 hours, and they were paid $10 an hour. So they got paid $40 for their participation. Those that did not consume alcohol, they only took 2 hours to go through the experiment. They did not consume alcohol, and then they went through the experiment, and then after that, they could leave. They could go home because they didn't need to sober up. And they got paid $20 for their participation. And participants knew from the very beginning when they, before they started the experiment, they were told how much they were going to be paid. They were told they're going to get paid $40 or $20. Well, guess what? Those that were paid $20, or those that found out they were going to be paid $20 and not $40, well, they were upset, you know, because they had potentially they could have been paid 40, but they were being paid 20 instead. They were told you might get paid $40, you know, $20, and they were told they were going to be paid 20. Well, that made them upset. And those were the ones who were not consuming alcohol. They didn't need time to sober up afterward. But what happened is that we found that the ones that were not consuming alcohol were actually behaving more aggressively than the ones that did. And we were confused. We expected the alcohol group, those that consume alcohol, to be more aggressive. But it turns out we had a confounding variable. We had the payment affecting the aggressive behavior. Those that were getting paid $20 were behaving more aggressively because they were getting shortchanged, so to speak. They believed they were getting shortchanged and being paid only $20 when they could have gotten 40. So we had a confounding variable, which was the amount of payment participants were given. And we were not aware at the beginning that that was going to be a problem. We identified the confounding variable. We have identified the other thing that was messing up the experiment, which was affecting the results, and then we changed it. What we did is basically we had participants go through the experiment. Some of them consumed alcohol, some of them did not. And they were paid at the end, but they didn't find out how much they were going to be paid until the experiment was over. Then they found out that, okay, took you 4 hours to get through the whole thing. You get paid $40. It only took you $20. 2 hours, you get paid $20. And they only found out how much they were going to be paid at the end. And after that, they can get as upset as they want. No big deal. The experiment's over. We already got their results. So you see, we fixed that problem. But long story short, a confounding variable is just some other thing that could be affecting the outcome of the experiment, that is messing up your experiment, or potentially giving you the results that you want, but it's not because of what you predicted. So a confounding variable is just some other variable, some other thing that's affecting the outcome. And you don't want that. What you want is for your experiment to work out the way you planned. Another problem with an experiment, a potential problem, is selection bias. You need to be careful when you recruit participants for your experiment that you do it in a way that's not biased. I'll give you an example again with the alcohol study. When we selected participants, when we recruited participants for the alcohol study, we put an ad in the school newspaper. And we said participants needed for a study. We'll pay, you can be paid $10. You will be paid $10 an hour for your participation. The ad said something like that. Okay, we wanted to recruit participants, and we wanted them to participate in the study. We wanted them to, their motivation for participating in the study, we only wanted it to be that they wanted to get paid. Now, but what if we had put an ad in the school newspaper that said participants needed for an alcohol study, for a study on alcohol, pays $10 an hour? What if we put an ad like that out there? What would happen is that we would get a whole bunch of participants calling who love alcohol. We potentially would get a bunch of alcoholics, a bunch of problem drinkers signing up for our study. And that would be a problem, because then what we're actually doing is we're doing a study only using alcoholics, or maybe not only alcoholics, but we're going to get a bunch of alcoholics in there. And that was not our goal. Our goal was to determine how alcohol affects aggressive behavior in everyday people, not alcoholics. We don't want a biased sample. We don't just want a group of people who loves alcohol. Okay, we want the normal participant that can legally drink, not alcoholics. So you have to be careful when you select participants for your study or you recruit people, so you're not recruiting just a certain kind of people, just like you wouldn't just want, for instance, Republicans in a survey about, whether they plan to vote for Donald Trump. You want Democrats in there too. If you want to really see how people, whether people plan to vote for Donald Trump, right? You need a sample that is going to, have a variety of voters. Same thing with an experiment. You want your sample, you want your group of participants to be, your average everyday people, and they could vary in different ways, but you don't just want a bunch of alcoholics. Okay, so you have to be careful with that selection bias. There's also potential experimenter bias. See, the experimenter knows the prediction for the experiment. Okay, the experimenter knows the predictions and what the outcome should be if it turns out as planned. So the experimenter has this hypothesis, right, that he expects that alcohol will lead to aggressive behavior. And because the experimenter knows that, he could, without knowing it, unknowingly or in some unconscious level, purposely make it so the experiment works out as he or she predicted. He or she might be a little bit mean to the participants that consumed alcohol to make sure they're more aggressive, and maybe a little bit nicer to those that did not consume alcohol. So there could be experimenter bias. In other words, the experimenter could knowingly or even unknowingly, even without intending it, could actually make the experimental results work out as he planned, or as he or she planned, in his or her favor. That's a potential problem. Okay, how do you do that? Okay, how do you fix that? We'll talk about that. There's also potential placebo effects. A placebo effect is when you have an effect due to expectations. So for instance, what if participants consume a drink and they believe it has alcohol in it? Well, then they will behave as if they're intoxicated when in fact they are not. That's called the placebo effect. Placebo effects can actually potentially mess up your experiments if you don't plan for them. Okay, so what you want is participants that have consumed real alcohol, that are really intoxicated. You want those to be the ones that behave more aggressively, not the ones that are taking the placebo, not the ones who think they are intoxicated, not the ones who think they've consumed alcohol. But there's a way to deal with that. But these are all potential problems. So that you can see there's a lot of potential problems with an experiment. But we're going to talk now about how you actually do an experiment, and in explaining that, you'll see that we can deal with a lot of these potential issues. Okay, so let's talk about how you actually do an experiment. Okay, the features of an experiment. Okay, an experiment has an independent variable, and it also has a dependent variable. An independent variable, okay, abbreviation IV, I'll just call it an independent variable. An independent variable is the variable that is changed or manipulated. So in an experiment, the independent variable is that thing that you're going to vary in some way. You're going to manipulate it in some way. In our example that we've been talking about, the independent variable is alcohol. We want to study the effect of alcohol on aggressive behavior. Alcohol is what we are going to vary. So, and I have a hint for you guys. There's this alcohol. Yes, no. So some people will get alcohol, yes, and some people will not get alcohol. That would be the no. Now, you also need in an experiment a dependent variable, a DV, okay? That is the variable that is affected by the independent variable. Usually that's some kind of behavior, but it doesn't have to be. So if you want to study the effect of aggression, if you want to study the effect of alcohol on aggressive behavior, what we're actually interested in measuring at the end is the aggressive behavior. The behavior is aggressive behavior. There's a simple way to remember this, okay? The independent variable is the cause and the dependent variable is the effect. If you want to study the effect of alcohol on aggressive behavior, Alcohol is the independent variable. Aggressive behavior, that's the dependent variable. That's the thing you measure afterward. So the independent variable is the one you vary, and the dependent variable is the one you measure afterward. Often a behavior, but not always. I'll give you another example. If you want to study how memory is affected by marijuana, then your independent variable is marijuana, and your dependent variable is memory. That is how that works. The independent variable is the variable that you change, you manipulate, okay? And the dependent variable is the one you measure afterward. Simple way to think about that, like I said, the independent variable is the cause, dependent variable is the effect. Okay, moving on. There's more to an experiment. In an experiment, you also have an experimental group, also called a treatment group. The experimental group is the group of participants that are given in a non-zero amount of the independent variable. Let me explain that because that sounds a little technical. The experimental group are those participants who get something, okay? They get some amount of the independent variable. If we're talking about alcohol, these are the individuals who get some alcohol. That is your experimental group, your treatment group. The control group, or the no treatment group, that one's easy to understand. That's the group that's given a zero amount of the independent variable, The control group doesn't get any alcohol. And why do we want a control group? Why do we even need that? Why do we want to run a bunch of people through the study that's not going to get any alcohol and then see how aggressive they are? Well, because we need to compare with the experimental group. If alcohol really works, then those that consumed it, those that are in the experimental group, should be more aggressive than those in the control group, than those who didn't get any alcohol. Now, we can also have a placebo group. I said that a placebo effect can be a problem, okay? Potentially mess up your study, your experiment. Well, if you have a placebo group, then it's not so much of a problem because then you can see what it's doing. A placebo group is the group of people who's given an inactive substance that can be confused with the independent variable. Let me explain that. The placebo group is a group of people that's given something that doesn't really do anything. They're given a placebo. If we're talking about alcohol, the placebo group, they get something that's not real alcohol. My example here, it might be non-alcoholic beer. They get something that doesn't really have alcohol in it. Might taste like alcohol, look like alcohol, maybe even smell like alcohol, but it's not alcohol. Okay? The placebo group, they get something that's fake, something that's phony. Okay? And if alcohol really does increase aggressive behavior, what you should find is that your experimental group, those that got alcohol, they should be more aggressive than those that did not get alcohol. They should be more aggressive than the control group. Okay, they should be more aggressive than that. And those that got alcohol, the experimental group, right, they should also show more aggression than those that were given a placebo. Those that got some phony substance, some inactive thing that is not alcohol. That way we can compare the different effects. What you usually find is the experimental group was the most aggressive of all. And then the placebo group was the second most aggressive. And the least aggressive was the control group who got nothing, basically. They got no alcohol. They did not get a placebo. The placebo group might show a little bit more aggression than the control group because some of them might believe that they're actually getting real alcohol. Those are the features of an experiment, okay? So you need an independent variable, you need a dependent variable, you need an experimental group, and a control group. You don't always need a placebo group, but if you want a good experiment, if it's possible, you can have one. Let's keep going. Oh, and it says there, by the way, do classwork, numbers 1 through 18. We'll do that after the lecture's over. There are different types of experiments. An experiment could be single blind, And that means that the experimenter knows the value of the independent variable, but the participants do not. Let me explain that. A single blind experiment is one in which the experimenter knows what the participants are getting. The experimenter knows if the participants are getting alcohol, if they're not getting alcohol, if they're getting a placebo. The experimenter knows what's going on, but the participants do not know what's going on. They don't know what they're getting. They don't know if they're consuming real alcohol, fake alcohol. They don't know. They're kept in the dark. They're kept blind. That's a single blind study. Now, why would we want that? Why would we want a single blind study? Because, well, we don't want the participants to know what they're going to be getting. We don't want them to know that they really are getting alcohol versus a placebo, something like that. We don't want them to know that because we don't want participants to behave in a certain way just because they think they're getting something. Okay, so we want to keep participants in the dark. Now, even better would be for you to have a double-blind study. A double-blind study is a study where neither the participants nor the experimenter know the value of the independent variable. So the participants don't know what they're getting. They don't know whether they're getting real alcohol or fake alcohol, for instance, real alcohol or a placebo. And the experimenter doesn't know either. That would be even better. Why would we want the experimenter not to know what participants are getting? Well, because that way we can get rid of experimenter bias. If the experimenter doesn't know who's getting real alcohol and who's not getting alcohol, then the experimenter has no choice but to treat all participants the same. The experimenter could not deliberately or even unknowingly make the results work out in his or her favor. Okay, we'll do the classwork problems in a little bit. Let's keep going. Okay, so that was the experiment. Now we're going to talk about analyzing results. We need to know a little bit about how to analyze results. And this doesn't just apply, by the way, to experiments. This applies to, case studies, surveys, observations, cross-sectional studies, archival studies, longitudinal studies, experiments. It applies to all of these research methods. Okay, so we did a study, and now what do? Well, when we do a study, if it's what we call a quantitative study, meaning that there's numbers involved, then there's usually some data. We get what we call some data. There's always data, actually. Okay, so one thing we can do after we do a study is look at the data, analyze the data. Okay, one type of analysis that we can do is to actually just engage in what we call description. We can use what are called descriptive methods when it comes to analyzing the data. We can just use description. Okay, we can just describe what we found. Okay, so one thing we can do is we can look at the average. What is the average amount of aggression that we saw in our participants? What is the average age of participants? Or what is the average level of intoxication? All those things. Or if we ask, for instance, participants, let's say in a survey, we ask them, how many alcoholic drinks do you consume on a given day? We can calculate the average. In order to calculate the average, basically you add up all the participant responses and you divide by the total number of participants. Don't worry, you're not actually going to have to do any math for this, for this class, but you should know what a mean is. The mean is just the average, okay? Now the median is the middle number. That's a little bit hard to describe. The median is basically requires that you put your scores in order, and then you pick the middle number. The median is similar to the average, except that it's just the middle number. It's whatever number's in the middle. The percentage. You can also report the percentage. What percentage of participants, for instance, are male? What percentage are female? What percentage are Black, white, Latino, etc.? What percentage of participants, behaved aggressively, or were above a certain level of aggression? We can do that. We can report percentages. We can report totals. What's the total number of participants? How many males in our study? How many females in our study? Those are all things that we can do, that we can report. So that is just description. We're just describing what we found. That's all we're doing. We're not really explaining it. We're just describing it. Now, something that's a little bit harder to do is, when it comes to analyzing results, is engage in something called inference. To infer from our data, to infer something from our data, not just to describe our data, not just to describe percentages, means, and standard deviation. Actually, yeah, I'm telling you a little bit more that was not mentioned there, but not just to describe percentages, right? Not just to describe averages and things like that, means, totals, percentages. We can do more than that. We can infer something from our data. And what that means is that we want to determine something by looking at data. We want to make some conclusion from our data. We want to test something. One thing we can do is we can determine whether there's a difference between group 1 and group 2. If there's a real difference between group 1 or group 2. If there is a statistically significant difference. So in other words, in an experiment, we can determine if there's a difference between those that consumed alcohol and those that did not. That would be for us to make some kind of inference. So in an experiment, the treatment, the alcohol, actually has an effect if we find that there's a difference between the treatment group and the no treatment group. And we find that that difference is statistically significant. That is a little bit harder to do than just describing your results. So here, you're not just describing what the averages are. What you're actually trying to determine if there's a difference in the average of one group, let's say those that consumed alcohol, and the average of another group. So if there's a difference between those that consumed alcohol and those that did not, and is that difference statistically significant? Is that difference big enough to matter? In other words, is that a real difference, or is it something that is so small that it's likely due to chance? I'll give you an example. If we find that the average level of aggression, let's say for those that consumed alcohol, on a scale of 1 to 5, let's say is 4, and then we find that the average level of aggression for those that did not consume alcohol on a scale of 1 to 5 was a 2. The difference between an average of 4 and an average of 2, is that big enough to matter? It probably is, okay? One number is twice as large as the other. And if we were to actually run some tests that you don't have to know yet in this class, because this is an introductory class, if we were to run some tests to determine if the difference is real or not, if it is statistically significant, we would find that that's a real difference. That 4 is definitely larger than 2. It's a real difference. It did not occur by chance. But what if we found that let's say the aggression of those that consumed alcohol, let's say, was a 3, and then the aggression, the average level of aggression for those that did not consume alcohol, was maybe like a 2.8 or something like that. There's a tiny difference between the groups. That difference is probably not big enough to matter. It's probably not statistically significant. And if we were to run some tests, we'd probably find that that's the case, that it's not a real difference. So that's another thing we can do. We can infer something from our data. We can determine if there's a real difference between one group and another. That involves a little bit more work. Another thing you can do that we're going to spend more time on is determine if there is a correlation between one thing and another. We can determine if there's a correlation, between variable 1 and variable 2, for instance. We can determine if there's a correlation between one thing and another thing, that there is some association. some relationship. That's what we mean. Now, in order to determine if there's a correlation, we have to know about something called the correlation coefficient. The correlation coefficient is a number that we abbreviate as R, and that number is between -1 and +1. So R is the correlation coefficient, and it's a number between -1 and +1. And that number tells us how things are related. If the number is positive, that means we have a positive relationship or a positive correlation, like R equals 0.51. When the number is positive, we don't have to put the plus, okay? If the number is negative, if R is negative, then it tells us that we have a negative relationship. R equals -0.63. That tells us the relationship is negative. The correlation is negative, okay? If the number is close to 0, that means there is no relationship. If R equals maybe 0.03, some number like that, that number is pretty close to 0. That means there's no relationship, no correlation between those two things. Now let me explain that further so you understand, because I know this, you might not understand this yet, but I'll give you plenty of examples. So let's keep going. Now, in order to determine, so all we've done here is describe what the correlation coefficient is, a number between -1 and 1. And we said if the number is positive, it's a positive relationship. If the number is negative, it's a negative relationship. If the number is close to 0, that means there's no relationship. Okay, that's what we've done. Determine if it's positive, negative, or no relationship. We can also determine the type of relationship we have by looking at what we call a scatter plot. A scatter plot is a graph, basically, that illustrates the type of relationship between those variables. A scattered plot. So it's a plot of a bunch of points that are scattered in some way. And you can see one there. So this graph that we're looking at here is showing us a positive relationship. We talked about, what a positive relationship is as far as the number, right? If the correlation is positive, if the number is positive, that means we have a positive relationship. But what does a positive relationship look like if you graph it? And this will really help us understand what a positive relationship is. With a positive relationship, what that means is that as variable 1 increases, variable 2 also increases. If variable 2 decreases, variable 2 also decreases. So with a positive relationship, what we have is that the variables increase together or decrease together. They move in the same direction. So you can see over here, here's a plot of some points. If we look at one of those points, let's say the one at the very top and the upper right, when variable 1 is 10, it's about 10 there. If we go all the way to 10, we go to variable 2, see how far it goes. Variable 2 is about 10. The point is 10 over here for variable 2 and 10 for variable 1. We can go lower when, over here, when variable 1 is 4. Let's go up, find a point there. When variable 1 is 4, variable 2 is 4. So you can see when variable 1 is high, so is variable 2. When variable 1 is low, so is variable 2. Let me look at another point just to make sure you understand, okay? Because the numbers don't have to be the same. Let's look over here over here, 8, right here. When variable 1 is 8, look, go up, find a point there. First point you find there, when variable 1 is 8, variable 2 is about 7. Okay. And right here, when variable 1 is about 1, variable 2 is 1. So the point about positive relationships is that if one number is high, the other is also high. If one variable is low, the other one's low. If the variable is high, the other is high. So that's what we mean by a positive relationship. And I'll give you some examples in a bit so you understand. Now, a negative relationship. With a negative relationship, If one variable is up, the other one is down. If one number is high, the other one is low, okay? So with a negative relationship, the variables move in the opposite direction. So you can see over here with a negative relationship, when you plot the points, they form a graph that looks like this. So you can see if we look at variable 1, and we see over here variable 1, let's start at number 2 there. When variable 1 is 2, let's go up. When variable 1 is 2, we find a point there. There's one point there that says when variable 1 is 2, then when variable 1 is 2, then variable 2 is 8. Okay, so when variable 1 is low, it's only 2. Variable 2 is high, it's 8. We look this way. When variable 1 is high, we look over here. Variable 1 is 8. And now variable 2 is only about 2. So a negative relationship means that one variable is high, the other one is low. That's what that means. And I'll show you some examples in a bit. Now, when there's no relationship, when r is close to 0, when you plot the points, they'll look something like this. When variable 1 and variable 2 are not related, that means the relationship is close to 0. You plot the points, and it looks something like this. The points are scattered all over the place. It's random. I'll give you an example. When you look at the craters of the moon, there are craters all over the place. The moon has been struck by meteorites in a lot of different places, all over the place. And there doesn't seem to be a pattern. They're just all over. The chances of the moon being hit by a meteor in one part of the moon versus the other seems to be random. The craters are all over. Same thing with this plot here. The points are all over. There is no actual, there is no logic to this, actually. There doesn't seem to be any pattern, I should say. You can't really draw a line to these points. Whereas if you look at the previous one where there's a negative relationship, you can draw a line through those points. And I will tell you, the line you draw has a negative slope. There's a negative relationship there. If you look at the graph for a positive relationship, you plot the points there, draw a line through those points, you have a positive slope. But when you look at the line, when you look at no relationship, you can see the points are all over the place. You can't really draw a line going one way or the other that really seems to capture most of the points. So there's no relationship. Variable 1 and variable 2 are not related. Let me give you an example now so you understand, okay? Let me start with variable with a positive relationship. There is a positive relationship between income and health, believe it or not. That's not a good example. There's a positive relationship. Let me give you one that's not related to psychology so it's easy to understand. There is a positive relationship between income and car ownership. In other words, the more money you make, the more cars you own. As you guys know, most rich people don't own one car. They own a whole fleet of cars. They might have a dozen cars and all expensive cars. The less money you make, the less cars you own. If you make very little money, if you're poor, maybe you own a car, right? Might not be a very good car, but you probably own a car. But if you're really poor, you might not own a car at all. If you're middle class, you might have a couple of cars. One for you, one for the wife, or one for the husband, one for the wife, and maybe even a car for the teenager or something like that. You might have 2 or 3 or something like that. But there's a positive relationship between income and car ownership. The more income you have, the more cars you own. That would be a positive relationship. So the more income you have, the more cars you own, but also the less income you have, the less cars you own. That's a positive relationship. If one thing is high, one variable is high, say income, The other one is also high, car ownership. If one variable is low income, then the other variable, car ownership, is also low. Now, a negative relationship is different. With a negative relationship, if one variable is high, the other one is low. An example of that might be, let's say, I think of an example here, because I have several in the classwork that we're going to look at in a moment. An example might be, for instance, let's say the cholesterol, your level of cholesterol. Now, let me put it this way. Okay, an example might be relationship between weight, let's say, and longevity, how long you live. If your weight is very high, you're probably not going to live very long. Okay? If your weight is lower, you'll probably live longer. That's an example there of a negative relationship. The more you weigh, the shorter usually your lifespan. The less you weigh, usually the longer your lifespan. Assuming that you don't starve to death, by the way. Now, there are extremes like anorexia, which that wouldn't help. People who are anorexic actually can starve to death, but let's leave out the extremes, okay? Okay, usually the more you weigh, the less healthy you are, the shorter your lifespan. So the more you weigh, usually the shorter your lifespan. And the less you weigh, usually, being thinner is healthier, the longer your lifespan. Let me give you another example that's actually even easier than that to understand. The taller you are, the more you weigh. Oh wait, no, that would be a positive relationship. Okay, never mind that example. The one I mentioned earlier, the one about weight and longevity is a proper example. Okay, so the more you weigh, usually the shorter your lifespan. The less you weigh, usually the longer your lifespan. Some of you might be thinking, hey, that's not really true. Okay, I mean, you can, I weigh like 200 pounds. I'm like 6'5". That doesn't mean I'm going to die soon, right? No, not necessarily. It's a correlation. Okay, it's basically telling you that things are associated. Here's the thing: you have to be careful with correlations. It's not cause and effect. Okay, necessarily. This is just we're just looking at a relationship here. There are people who are tall who are also thin, and may weigh more than people who are shorter and maybe a little bit more overweight. So this is an average, okay? When we're talking about these things, it's based on a bunch of points, not based on one individual or one point, okay? But usually, the more people weigh, put it this way: the more overweight you are, usually the shorter your lifespan, okay? The less overweight you are, the longer your lifespan. Okay, being obese will shorten your lifespan. Okay. Now, no relationship means R is close to 0. No relationship there. You plot the points. It looks something like this. So an example would be, the relationship between, let's say, your height and your intelligence. Your height says nothing about your intelligence. If you're tall, that doesn't mean you're intelligent. It doesn't mean that you're unintelligent either. There is no relationship between those two things. So in other words, if we know one thing, it tells us nothing about the other. So no relationship there. With no relationship, we mean that if we know one thing, we know nothing about the other. With a negative relationship, what that tells us is if we know one thing, we can predict that the other one's low. If we know, for instance, that you are very overweight, obese, then we can predict to some extent that your lifespan will probably be shorter. It doesn't always work out that way. It's a prediction, and there is some accuracy to that, but it doesn't work out for everyone. And with a positive relationship, right, the more income you have, we can predict that, well, you probably have more cars. So this is really about predicting. Positive relationship. If two things are related positively, we know one thing, we can predict the other thing, and they usually move in the same direction. With a negative relationship, we know one thing, we can predict the other thing, and it's usually in the opposite direction. And with no relationship, If we know one thing, we know nothing about the other. Okay, now we need to know about the strength of a relationship. The strength of a relationship, okay? The strength of a relationship is indicated by how tightly clustered the points are around the line. So I told you guys before that R is a number that varies between -1 and +1. So 1 is about as strong as the relationship could be. So if we look there at the first one there on the upper left, we have a line there that's perfectly straight at an angle there, perfectly straight line. Now there are points that cluster along that line, but you can't even see them, that they are perfectly along that line. The relationship is 1, that means it's perfect. That means that if I know one thing, I know exactly what the other thing is going to be. If I know, for instance, now the relationship, I did mention, now this is also a positive relationship. You can see it has a positive slope. It's a positive relationship, +1. So what that means, if I know one thing, I know exactly what the other thing is going to be. So let's say that if there was a positive relationship, if there was a perfect positive relationship between weight and longevity, then that means that if I know your weight, I know exactly how long you're going to live. That's what that would mean. However, the relationship between weight and longevity, how long you're going to live, is not perfect. So it's not that perfect. But if it was perfect, that's what that means. If I know one thing, I know exactly what the other one would be. Now here we have R equals 0.9. It's also positive. And you can see there the points clustered along that line. They are not perfectly clustered along that line. So that it's a strong relationship. That means that if I know one thing, then there's a very good chance I know the other. What are the chances? Well, you have to square that. Square 0.9 and you get 0.81. And what that means is that if the relationship is 0.9, if I know one thing, then I'm 81% sure I can predict the other. And now we have R equals 0.8, and you can see the points are even more scattered. That means if I know one thing, there's a 64% chance I can predict the other thing. 0.8 squared is 0.64, 64%. We go to R equals 0.7, points a little bit more scattered. R equals 0.6, more scattered. And you can see the points are getting more and more scattered the closer we get to 0. R equals 0.4, 0.3, 0.2, 0.1, 0. When we get to 0, that means the relationship is 0. The points are randomly scattered. And if I know one thing, the chances that I can predict the other are 0. If I know one thing, I know nothing about the other. That's what a relationship of 0 means. So the stronger relationships will be closer to +1 and also closer to -1, which I'll explain in a moment. If the number is close to 0, that means there is no relationship. The closer the number is to 0, the closer the correlation is to 0, the weaker the relationship. Now let's go the other way. That's R equals -0.1, -0.2, -0.3. And you can see as we get closer and closer to -1, the points are more and more tightly clustered along that line. -0.4, -0.5, 0.6. When we get to R equals -1, you can see that again, the points are perfectly clustered along the line there, except now it's a line with a negative slope. And what that means is that if I know one thing, I know exactly what the other thing is going to be, except that it will be low, or it will be the reverse, I should say. So if I know, let's say there's a perfect negative relationship between weight and longevity. Let's just assume that. I know it's not true, but let's assume that. If there was a perfect negative relationship between weight and longevity, that means that if I know your weight, then I know exactly how long you're going to live. In this case, though, the more you weigh, the longer well, in this case, actually, the example works, but in this case, the more you weigh, the less you're going to live. You know, I misspoke earlier with the perfect positive relationship. A perfect positive relationship there of R equals 1 means that if I know one thing, I know exactly what it's going to be, but it means that they move in the same direction. R equals 1. So here's the thing. There's where I have to make the assumption. Let's assume that there's a perfect positive relationship between weight and longevity. That would mean that if I know how much you weigh, I can predict, you know, with 100% accuracy, how long you're going to live. But in this case, since the relationship is positive, it would mean that the more you weigh, the longer you're going to live. If the relationship is negative, that means the less you weigh, the less you're going to live. Okay, so how tightly clustered the points are on the line tells us the strength of the relationship, and you can also tell by the number. Okay, a correlation with a number that's close to positive 1 is a stronger relationship than one that's closer to 0. And a correlation that's also closer to negative 1, it's also stronger than one that's close to 0. So you're going to have questions like this on your homework and on the exam. Okay, like which one of these is the strongest relationship? Is it R equals 0.51? R equals negative 0.67? R equals 0.20? R equals 0.03? In this case, the strongest relationship is R equals negative 0.67 because it is the one that's furthest away from 0. Which one is the weakest relationship out of all those? It would be R equals 0.03. It's the one that's closest to 0. So as the numbers get closer to 0, that indicates a weaker relationship. As the numbers get further away from 0, that's a stronger relationship. So the stronger relationship isn't always the positive one. It isn't always the negative one. It's the one that's farthest away from 0. Okay? Keep that in mind. All right. Now, you can play around over here. If you click on this link, you'll be able to play around with the correlations, make it stronger, stronger, weaker, and play around with it so you understand. But I'll tell you that I can't show you guys here because it doesn't work when we're using Zoom. If I click on this link, you'll see a black screen. But you can play with it on your own. We usually don't have time to show you in class anyway. A point I want to make here, I already mentioned it, but I want to mention it again. Very important weight. Correlation does not equal causation. Just because two things are related doesn't mean they cause each other. So for instance, there is a, like I mentioned earlier, the correlation. There's a correlation, let's say, between weight and longevity. Okay, the more you weigh, usually the shorter your lifespan. Does that mean that it's the actual weight that's causing you to live less, or that's causing a shorter lifespan? Probably not. There are people who are tall who weigh a lot, and that doesn't necessarily mean that they're not going to live that long. What really is, okay, what's really causing the shorter lifespan will be things like cholesterol and fat and high blood pressure and heart disease and all those things that are likely are more common in people who are obese and overweight, the people who weigh more. That's what's actually causing the shorter lifespan, not the weight itself. So the point is that correlation tells us that two things are related, but not necessarily, that they don't necessarily cause each other. They might or they might not, okay? Correlation does not equal causation, okay? In order to determine that something causes another, we need an experiment. Simply determining that two things are related does not tell us that they cause each other. Another example here, maybe one that's easier to understand. Does eating cereal actually cause someone to be healthy, to be a healthy weight? No, not necessarily. But if you do a study, you do a survey, you'll find that those who eat cereal weigh less. But the cereal is not actually making them weigh less. The reason those that eat cereal weigh less is because those that eat cereal tend to be children and people who are younger. Adults usually don't eat cereal that much. So you can see there's a correlation between eating cereal and weight, but eating cereal doesn't affect your weight. As a matter of fact, a lot of those cereals are actually bad for you. But children usually eat cereal more and they weigh less. So there's a correlation between eating cereal and being a healthy weight, but it doesn't mean the cereal is making you, the cereal doesn't cause the weight, is what I'm saying. We'll go through several examples in a moment. So correlation does not indicate cause and effect. There could be a confounding variable, something else that's causing the relation. In the case of cereal and healthy weight, what's actually causing the weight is actually the person's age. Children weigh less, and they also eat more cereal. There's also illusory correlations. Okay, many people believe that the moon actually makes you the moon makes you behave oddly, and that's where the word lunatic comes from. You know, the word luna means moon in Spanish. Lunatic, someone who behaves oddly, that's crazy in some way. Okay, but the moon has nothing to do with your behavior. Okay, it's what we call an illusory correlation. It might look like maybe there's some relationship there, but there's not. It's an illusion. There's no correlation. It's a false correlation. An illusory correlation or a false correlation occurs when people believe that a relationship exists between two things when no such thing exists. And this is related to what I might have mentioned before. Some astrology, for instance. Maybe I didn't mention it in this class, but astrology. You know, there's people who believe that the position of the stars somehow has to do with their future, their behavior, what's going to happen to them. No such thing exists. That's what we call an illusory correlation. There's no real correlation there. If you were to measure it, map things out, you'll see there's actually no pattern there. And that's it. I will stop recording.